This is a joint work with Serge Fehr. As we all know, as of 2016, the US National Institute of Standards and Technology, NIST, initiated the post-quantum standardization process. Last summer, they finally announced 4 winner schemes for the round 3. However, for the sake of variety, there is an additional call for the digital signature scheme. This summer, July, they announces, I think 40 on-ramp candidate schemes for this extra round. The talk today concerns one of the candidates, namely Hawk. It is a post-quantum signature scheme based on the probabilistic Hessian sign using the lattice isomorphism problem. The lattice isomorphism problem framework is firstly proposed by Leo Dugas and Wessel van Woerden in 2022, based on which the same year AsiaCrypt 2022 Hawk is proposed. Later, it is submitted to NIST as one of the, I think, 7 lattice-based signature candidates for the extra round. One main advantage of Hawk is its simplicity. In particular, the discrete Gaussian sampling, which is usually the efficiency bottleneck for a lattice-based signature scheme, is performed on a very simple lattice, namely integer lattice in Hawk. And because of such simplicity, Hawk is among one of the most efficient candidate signature scheme. In particular, among all unbroken scheme and in all parameters, it now has the fastest signing speed for now. Furthermore, Hawk is suitable for various devices, including low-end devices. In particular, it doesn't require floating point arithmetics as opposed to its conceptual predecessor, Falcon. Moving on to the security of Hawk, in order to recover secret key, one is required to solve the so-called lattice isomorphism problem. What about the unforgeability, in particular against chosen message attack? Well, Hawk follows a non-standard variant of Hessian sign, for which there is no off-the-shelf theorem nor generic analysis to apply. In particular, it's also worth noting that it doesn't fit into the framework of trapdoor one-way function, nor the GPV framework of preimage sampleable function. In the Hawk paper, the classical unforgeability in the random oracle model is reduced to the so-called one more SVP problem, which we will explain later. However, this analysis does not carry over to the quantum setting. So today, this work we are presenting, we analyze the quantum security of Hawk, in particular, reducing the unforgeability in the quantum random oracle model to the very same one more SVP problem. Our analysis is modular and accessible to even non-quantum experts. Furthermore, by replacing certain quantum component within the proof into its classical counterpart, one immediately obtains a classical proof that is easy for verification. As we mentioned earlier, the discrete Gaussian sampling in Hawk is performed on a very simple lattice, in particular just integer tuples in the Euclidean norm. from which, given a basis matrix B, and it's going to induce a grand matrix Q, and thereby multiplying with the matrix B, one can shift from the discrete Gaussian sampling in the Euclidean norm to a discrete Gaussian sampling in the Q norm. And therefore, given this basis matrix B, it is easy also to sample discrete Gaussian sampling in the Q norm. However, if one is only given the grand matrix Q but not the basis matrix B, it is at least believed to be hard in order to find a short vector in the Q norm. Even when the adversary is given additional discrete Gaussian samples in the Q norm, in which case the adversary, of course, needs to find a fresh short vector, where the freshness means it cannot be somehow easily derived from existing samples. What's used in the signing procedure of Hawk is a slightly twisted discrete Gaussian distribution, namely on a shifted lattice by the binary vector H, as you can see on the slide. This discrete Gaussian distribution on the shifted lattice can be thought of as performing the discrete Gaussian sampling in the Q norm, but post-selecting the outcome vector such that it falls into the shifted lattice. And now the signing procedure of maybe a little bit oversimplified Hawk goes as follows. As most of the probabilistic hash and sign signature, it first hash the to-be-signed message with a randomized sort and get a lattice vector H with binary coefficient. Later, using this binary vector, sample according to the shifted discrete Gaussian sampling and get a short vector in Q norm, a short vector V, from which computing the vector S, which is half of the H plus V, and producing the signature as the vector S together with the random sort. We further note that the vector S, despite obtained by half of some vector, is always an integral vector. This is because the corresponding discrete Gaussian sampling, you can see on the shifted lattice, must have the, for every vector within the support, it must have the same parity as if the vector H. Already from this oversimplified Hawk, one can see that if there's an attacker that forges a signature from scratch, then he would need to construct a short vector in Q norm. This short vector can be extracted from any valid signature. However, there is a forgery attack by given existing signatures, which is done by inverting the sign of the corresponding short vector V and computing the rest of the signature consistently. To mitigate this forgery attack, Hawk also introduced an unique representation of the short vector V, which does not distinguish between the positive or negative sign of the short vector. One may be tempted to further forge a signature by not just inverting the short vector V, but multiplying a sort of geometric unit to the short vector that doesn't affect the Q norm, But as can be shown in the analysis, after multiplying this geometric to the short vector v, almost always the corresponding vector s is going to be non-integral and therefore rejected by the verifier. Next, more detail about how we prove the security of Hawk. The goal is to simulate this sign-in oracle while still being able to show the extracted short vector v is fresh as long as the forgery itself is fresh. The simulator is given discrete Gaussian sample as in the one more SVP challenge, and by reverting the order of generating the transcript, namely first producing the short vector v via discrete Gaussian sampling, and computing the rest of the signature consistently, after which reprogram the transcript to the random oracle. That's how the simulation works. To show the security of Hawk, we need to show two steps of argument. First, we show the closeness in between the real transcript from the simulation of the signature. And second, we show that a fresh and valid forgery produced by interacting with the simulation should always yield a short vector v that is fresh, as in the one more SVP game required. We note that both steps require quantum reasoning, but for this talk, I'll only zoom into the first step. To show that the simulation cannot be distinguished from the real transcript, we introduced an intermediate oracle, which we refer to as the transcript oracle. The transcript oracle basically replaces the hash evaluation of the signing procedure into first sampling the output binary vector h freshly and then reprogram to the random oracle. From this intermediate oracle, we show the closeness in two steps. In the first step, the closeness in between signing oracle and the transcript oracle can be shown by the so-called quantum adaptive reprogramming lemma, which on a conceptual level argues that a reprogramming cannot be noticed as long as prior to a reprogramming, the input where it's being reprogrammed has not been queried to the random oracle. And on the second step, where we show the transcript oracle is indistinguishable from the simulation, we do a statistical argument by bounding the relevant transcript being statistically close. This line of reasoning can be further improved by the Ren-Yi's divergence arguments, but please look at the Hawk specification for more detail. Finally, after obtaining quantum proof, we can replace certain quantum component into the classical counterpart, and from which we obtain classical proof. Namely, the two components we need to replace are first replacing the quantum adaptive reprogramming lemma to its classical counterpart, which is easy by simply defining a bad event that there has been a query made to the reprogrammed input prior to the reprogramming. And second, we replace the hardness for quantum attacker to find a hash pre-image into its classical counterpart, which is also easy, no, not easy, but which is already a well-understood question. As conclusion, Hawk is quantum secure, at least as secure as it's classically proven to be. Please look at the full paper for more detail. Thanks.
Thanks for your talk. I'm curious about the concrete bounds that you obtained. How tight or non-tight is your QROM proof?
The concrete bound, yes. I think there's for quantum or classical?
For quantum, for your proof in QROM.
Yes, I think in quantum there's a QH times square root Q as epsilon, where epsilon is the length of the entropy of the salt, and QH, QS are the queries to the random oracle, and QS is the queries to the number of chosen messages. I think that's the dominating term. There are some minor terms which I cannot remember on the spot. But for the tightness, it's also worth noting that this is non-tight, at least not for Hawk, by noticing that even when an attacker come up with one more SVP, right? Even if an attacker can somehow find one more SVP, it is still hard for him to forge a signature. So he still need to find some pre-image in order to do that. So it's believed it's not a tight reduction.
Oh, thanks. So just a small follow-up. So if you replace this quantum reasoning with classical reasoning,
yeah.
What happens to the tightness in the classical ROM? Is it still, do you get a tight proof in general, like tight reduction to one more recipe, or do you still have this QH term in the multiplicative?
In classical proof, whether that is tight or not, I'm not 100% sure, but I expect it's still, for the same reason as quantum, it's not.
Okay. Thank you.
No problem.
Thank the speaker again. All right, that's it for the morning.